Okay, good day, everybody. So we are now being recorded and we are starting our session. This time will be devoted to the review of the previously studied materials that we are going to that we covered this past week. Okay, so what is this? How do I get back? All right, so looks like we are back. All right, so now let's start with the first concept, right? So for now, we are not going to have, let's say, it's problem one, right? We're not going to have any particular slides. So, but we will go in a more or less chronological order to take a look at some important things that we have seen over the past like 3 sessions of lecture presentations. The purpose here of this session in particular will be to reinforce some of the concepts because those some concepts will be reoccurring, right? So to say, in our practice this semester. So, and then hopefully, so once we kind of like continue going in the course, we'll be able to see something that can be reused in the future, right? So I'll try to make a note of that. So say, okay, well, this particular concept, right? It happens to be present in, let's say, chapter number 15, but also it will be happening in other organic chemistry courses, or maybe it will be happening in, let's say, your medicinal practice, right? In your engineering practice, because organic chemistry can be like linked not only to medicine, but to engineering to some extent as well, right? So I'll try to make it sort of say equitable to lots of different majors. So, but for now, let's take a look at our famous transfers, right? So we'll start with electrons and then we'll be building, right? How are we going to be building? So we'll start with the electron transfer, then we'll take a look at how the electrons are transferred within a particle, right? Let's say, and then how the resultant particles can be transferred like within chemical reactions between chemical organic substances in this case, right? So the first one is going to be the good old electron transfer, right? So just kind of like, let's say, principle one or something like that, P1, problem one, name it whatever you want. It's like the freedom of choice is yours. So let's take a look at this like electron thing, right? So electron has the negative charge, which is kind of denoted with this dash on top of the letter E, by the way. So it's going to be basically a negative particle, right? So if you are concerned with the charges that will inevitably be generated in a lot of instances of chemistry, to say the least, you need to be able to handle electrons, right? And how they are added or subtracted from various chemical species. Let's take a look at some kind of like very general abstract things, right? Let's say we have some sort of particle A, for example, right? And then what it can do, it can, for example, accept or lose electrons. That's like what we have here, two options, right? We cannot do some kind of like multiplication with electrons, right? So that's impossible. We can have several electrons subtracted or added to the molecule, right? So, but overall, when we like think about the relationship between some compound and electrons, it's going to be either addition of the electrons to this particular compound or subtraction, right? So we need to be like concerned with the charges, right? So typically charges will be shown as superscripts, right? So unless it is a zero charge. So, which you need to know at this point how to figure out, right? So if you have some kind of like pure compounds, let's say, for example, like sodium chloride, think about that, right? What's the total charge on sodium chloride? It's 0. And it's typically not shown because it is kind of implied that it's supposed to be known by the person, as I say, versed in the art of science, right? So then what's going to be the total charge, for example, on K2SO4, right? So those things are supposed to be kind of like familiar to us because they stem from the previous chemistries, such as introductory general chemistry 1, 2, and so on, right? So the charge total here is 0. So and then maybe it's going to be a little bit of the kind of like cheat sheet for you. So if you don't see the charge, then oftentimes you can assume there's going to be a charge of 0, unless you are asked specifically, okay, well, please assign the charges, right? That will be generated. So, which sometimes you will need to do. So if you see maybe like pure metals, right, such as zinc by itself, right, without any designations, it will have the charge of 0, for example. So let's just kind of reinforce this and put the charges of 0 here. So salts, right, so just like pure compounds will be having the charge of 0. Pure metals, for example, or maybe you see some sort of, I don't know, like molecule of CO2, right? So at this point, so we know that it is just kind of like a molecule. It's not some sort of ion. So it will have a charge of 0 as well, right? So now, if we have the charge of 0, this particle or this substance, whatever it might be, is known as a neutral compound, right? Neutrally charged, right? Charge is 0. So now let's say we're going to add 1 electron here, right? So what's going to happen? So basically, you're going to add charges 0 and -1, right? 0 plus -1 becomes what? Becomes -1 total charge, right? So now this electron is added to the previously neutral particle, and then this particle now has a charge of -1, right? So charges are added. So maybe sometimes you will have something like this, right? So let's make it more advanced. So what if you have the negatively charged particle, and then this particle accepts maybe like 2 electrons, right? So think about this for a second. We don't quite have today the opportunity for some sort of group work, right? Because we don't have many people yet, and it might be kind of a little bit difficult considering the recording will be published later on. So, but anyway, so just kind of like maybe take a piece of paper and start doodling on your own, right? So it's always good to write chemistry, so because the exams are written, for example, in like some courses such as ours, right? Okay, so here you add the charges, right? So -1 plus -2. So -1 and -2 mathematically becomes -3, right? So consequently, the charge here will be will now bear the charge of 3 minus, right? So that's going to be your negatively charged particle. So that's the first case. The second case is the electron release, right? So maybe from some neutral particle B, let's say, the electrons will be lost. So we cannot say minus like 3 electrons, for example. We need to show the release of the electrons on the product side. So just kind of like think about that, right? So you can only put electrons either to the left of the chemical reaction, because technically it's still a chemical reaction, right? You do change the composition of the compound. So because electrons are the substance to some extent, at least. And if you, let's say, remove electrons from some atom, then you will change the composition of this atom, for instance, right? So technically, you face a chemical reaction here because it's about changing the composition of the chemicals, right? So here you go. So B0, let's say it loses an electron, right? So what's going to happen? So used to have the neutral charge. So now the resulting particle will need to counterbalance the loss of 1 negative charge by the production of 1 positive charge, right? And the release of 1 electron, right? So we don't say like -1 electron, we say +1 electron on the right side. Okay, so yeah, this is, I don't know what it is. So anyway, so now if you look at the charge balance, it will be balanced, right? So maybe now let's take a look at this. So B0, let's say it's going to lose 3 electrons, for example, right? We'll say, okay, B modified will be here, right? So the 3 electrons will be released or lost, right? So lost or added to the right side. So that's the same thing. Just think about how you will pay, let's say, $50 for groceries. It's going to be like subtracted from your wallet or added to some sort of grocery shop, for instance, right? So anyway, so here you need to counterbalance the loss of 3 negative charges, right, by creation of the 3 positive charges on the resulting B particle. So also, if you think about that, 0, let's say minus 3, right? Minus 3 electrons, in other words, becomes 3 plus. 0 minus -3, just kind of like think about this mathematically, becomes 3 plus. So it's one way to think about it, or just balancing the charges, right? So let's say 3 electrons are lost. So then it means that the 3 positive charges will have to be generated, right? 2 electrons are lost, then two positive charges will have to be generated in addition to whatever the particle has, whatever charge, right? So then, like oftentimes in chemistry, so it's a little bit of a shortcut here. We'll be looking at the case when we start with some sort of neutral particle. It loses electrons, for example, and makes like a positive charge, right? So which was the case with our good old hydrogen atom, which is represented like so. So this dot stands for an electron. Remember Lewis structures, right? Dots are electrons of some sort. So now we are going to generate, we're going to release one electron. One electron will be released, right? Or lost, in other words, by the hydrogen atom. So the hydrogen atom now will not be like an atom anymore. So that's going to be your atom, like hydrogen atom. So now we're going to make this H plus, right? So that's going to be the hydrogen ion. So, but it's going to be known in other words as a proton, right? So make sure you spell it right. So proton. So sometimes people like misspell it. So which is the case, understandably, with a lot of chemical terms, but kind of like try to make it clear. So yeah, because it's going to be good for you, good for the people who read it. So
Wait,
anyway.
I have a question. Sorry. So whenever you lose an electron, it's a proton. I mean, whenever you
Yeah, that's right. So yeah,
so,
in this particular case though, right?
okay.
So yeah. So
Okay.
if you think about some other particles, they can also lose electrons, but they will not be called a proton, right? So a proton is like by definition is a positively charged hydrogen, right?
Okay.
Used to be an atom of the hydrogen, lost an electron, became H plus. H plus is a proton.
Okay. Thank you.
Yeah. All right, good. So yeah, just kind of, yeah, it's a good thing, right? So just think about the specificity of the terms. Perhaps that's like a good thing to keep in mind, right? So like, let's say like not everything that is positively charged is a proton, right? So you can just call positively charged species just positively charged, right? So which we will see in chemistry. You can also call them cations, right? So that's possible. So think about K plus potassium, right? So good for whatever muscle function, for example. And like sodium plus, right? So that's going to be sodium cation, K plus potassium cation. So yeah, they're positively charged like a proton, but proton is specifically H plus. All right. So anyway, now let's move on to the chat message. All right. So what's on be on the exam? Yeah, we will have the special kind of review before exam one. So those will be organized sometime, let's say on the weekend, likely, or Monday, or like Wednesday before the exam. So we'll take a look at some kind of like specific things, right? That may show up on the exam. They will be on the review. All right, so yeah, good stuff. So now let's see. Okay, so we're going to move on to now so from the electron transfer, we're going to the bigger particles, such as protons, for example, and we're going to look at the proton transfer, right? So before then, let's take a look at some kind of necessary Lewis structures, right? And then see how they can interact with the proton, for example, right? So yeah, the proton can be transferred, right? So transfer can be, again, so you can think about it as the addition or subtraction of the proton, right, from some sort of like particle. So let's move to, let's say, part 2 or something like this, right? So no more electrons for now. Let's see. So here, again, so it's a little bit of a review of the general chemistries, right? So it's important to think about, okay, where else can protons come from, right? Except, okay, hydrogen loses an electron. So it's like a very specific process, like hard to come by, right, in the lab. So, but what's easy to come by in the lab is acids, for example, right? So acid, such as, for example, like HCl, is by definition a compound that generates a proton, right? So something to recall. So hopefully it's not a new concept at this point in your chemistry journey. So then it will generate a proton. So HCl makes H plus. What else can it make? So, well, not so many options. It will make the counter ion, right? So if the proton is positive, the counter ion will be negative, right? That's why it's a counter ion. So that's what you're going to make. Make sure it's balanced, right? So H and Cl, H and Cl. Okay, we have the 1H, 1Cl, 1H, 1Cl on each side. So that's your atomic balance, right? So then you're going to have also the charge balance. Total charge on HCl is 0. Total charge here between H plus and Cl minus is 0, and -1 becomes 0, right? So here's the charge balance. So the proton is generated by an acid. If somebody asks you, show like examples of how to make a proton. So here you go, right? So why would Cl be negative? And then yeah, the H is positive, the Cl is negative. So if you think about it, so that's what happens. So think about the bonding, right? So and then the concepts from this week, right? So it used to be a 1-to-1 share of electrons. Each atom is 0 charge, right? Total charge on HCl is 0 because of this, right? So then chlorine is more electronegative, and then here it goes. So that was literally kind of like one of our actual concepts from at least general chemistry 2. So, and it's called the arrow pushing, right? That denotes the transfer of electrons. So yeah, basically this entire electron pair moves to chlorine because of the electronegativity, right? So chlorine is more electronegative. It pulls the electrons towards itself, and H will lose its electron. Consequently, this is what is going to happen, right? So that's going to be your result, right? You have H, and H lost its electron, just an H right now. Okay, so, but if it loses an electron, previously being neutral, it will become positively charged, right? So chlorine was neutral previously, but now it gained 1 electron. That's why chlorine now becomes minus, right? So you can see that in many other examples of like acid dissociation. This was our dissociation, or specifically the donation of a proton dissociation. All right, so the proton was donated. So yeah, chlorine will not be like positive, right? So apparently, as we saw from this example, it gains an electron, becomes negatively charged, right? So chlorine will be positive if somehow H would be more electronegative, which is not the case, right? So if chlorine can lose its only electron that's shared in the covalent bond, then chlorine, yes, will become positive, which can be the case, but it's in more like advanced levels of organic chemistry, right? So for now, we'll just go with electronegativity argument. All right, so then like other things, right? So how else can we generate a proton? So maybe let's take a look at like HF, right? So same thing, so just a different atom. So again, so you can literally switch from chlorine to F, and you will have the same picture. That's something that you can like draw yourself, right? By the way, so then still you have H plus and F minus. Total charge is 0. So, and then also if you think about it, if somehow F becomes positive in this particular reaction, right, then you will have total charge of +1, and +1 becomes +2. +2 is not the same as 0, so there's no balance of the charge, right? Balance means equality of the charge on the left and the right side of your chemical reaction. So so good questions. So yeah, that's how the proton can be generated, right? So here we're just dealing with the donation of the proton or the loss, right, via dissociation process. That's going to be your dissociation right here. Very important term. We will encounter this like a lot, right? So now what else? So that is your like loss of proton, loss, donation, right, are all like synonymous in this context. Let's now move on to another case, which is going to be the proton gain, right? Proton acceptance. So let's take a look at some cases, right? So like acids, actually speaking of like terms, fundamental things, which you encounter like throughout any level of organic chemistry, right? It's acids, right? So what are the acids? Well, you need to know this, right? So these are the species that will donate a proton, right? So remember, so the final exams questions from like Gen Chem 2, right? So oftentimes there are fundamental questions because they're there for a reason, since those things encounter like again and again. So in your career, and yeah, that will be true about, for example, real life situations such as cancer treatment, right? So or ulcers treatment. So it's like about the proton. inhibition, proton formation inhibition, so that like it doesn't chew the lining of the stomach, for example, or some other internal organs. Well, if we're talking about ulcers and stomach cancer, right, then the excess proton generation like might be contributing to the cancer formation because the proton will be kind of like too much proton, too acidic of the environment, in other words, so that will damage the lining, right, of the stomach. So, and then that's what happens actually in organic chemistry, more specifically, right, on a kind of like more simple scale than cancer situations. So yeah, you will see how the presence of the proton can be like conducive to the breaking of the certain bonds. If you think about it, so if you break the bond, right, so then you kind of like destroy the like macro version of the compound that is made of like a billion of those bonds. So if you like destroy like 5 million of those, then you might as well get a little bit of the like hole in the stomach or something, right? So yeah, protons can be also, you can think about the like excess acid kind of like promoted denaturation of protein. So that's like about the H plus reacting with the protein structure and splitting that into smaller particle, right? That leads to the denaturation and the kind of destruction of the protein structure. So anyway, so now let's switch from cancer to something more palatable, such as proton acceptance, right? So we were looking at like very like specific, not specific, but very popular examples, such as maybe you have like NH3, right? What is NH3, right? From the general chemistry perspective, that's a base, by the way, right? So a very popular example of the base. So base will accept a proton. So maybe like this. And now we just need to kind of show what happens, right? So still total charge is 0 plus 1 becomes plus 1 total, right? So you must create the charge balance and the like elemental balance, right? So basically here you have N and then 4 H's. So just put them together, right? It's going to be NH4 with a positive charge, right? The positive charge will belong to like N technically, right? So, but it's okay to show it this way, right? So it's like a very common writing, right, pattern. So here you have it, right? So that is the famous lone pair there, double dot designation. So that will be able to make a covalent bond, right? So because if you look at this, that does look like a covalent bond almost, right? So 2 electrons are needed. So just like here for a covalent bond. So then it will be created. So between the nitrogen and the H plus, right? So basically from the arrow pushing perspective that we can introduce a little bit more, because why not? It's a practice session, right? So we can show it this way. Electrons move from where there are lots of them to where there is like less of them, or like none, right? Especially if we have the positive charge, we can clearly see the attraction here between those like negatively charged electrons and the positively charged H plus. So then you're going to make NH4, right? So if we kind of like make an excerpt here, so we used to have something like this, NH3, right? So then now N used to have like double dot here, right? So, but now let's imagine that we are going to, is there a reverse button? No, there is no reverse button. Darn. All right, so anyway, so now N loses one of those black dots, basically, right, towards H plus. So now H plus acquires 1 electron. Think about now the electron transfer, right? You can see already how the scaffolding happens. We started with the electron transfers. Now we continue with something like bigger particles, basically, right? So now this H plus accepted 1 electron and then became just H0, right? Neutrally charged hydrogen atom. And this atom like, can make a bond, right? So just like it could make it here, it will make it here with the nitrogen, except of instead of chlorine. Okay, so nitrogen in turn lost one of those electrons. So they say this black dot is now here, right? Rightmost. So 1 electron was lost by the total neutral compound of NH3, specifically by nitrogen. So nitrogen now generated a plus charge on itself. That's why we have NH4 plus, right? Shorthand notation, that's your Lewis structure with the charge, basically, right? So now you have it, right? So that's your basically like base, right? If you think about the terms, base accepts a proton and then you make what? So you make technically, again, previous chemistries, conjugate acid. Why is it an acid, you might ask? So because, well, explain it to yourself, right? So what are the acids? They will donate H+. Now you can like practice and then show for yourself, by yourself, how, for example, NH4 plus will behave as an acid by proton donation, right? So show the chemical reaction in this case. So then pretty much another one. So what else can we do? So H2O, right? So we did have the practice of that nature in class. So, but now let's take a look at some organic compound, something a little bit more exciting. So I'm going to erase things here. Actually, I'll erase everything. Okay, let's see. Clear page. Okay, that's convenient. So part 3. Here, let's take a look. So what else do we have? So let's take a look at something actually that fuses your knowledge right now of like alkanes and the functional groups, right? So, and then there we can introduce the proton transfer. So it's like a very common chemical reaction, which we need to keep in mind. So, all right, let's see. Yeah, which is a very common chemical reaction. So now we're going to look at the like amine functional group. So if you think about it, so you used to have NH3, for example, right? So what is amine? That's when we have NH2 combination of atoms attached, for example, to an alkane or alkyl chain, right? So let's think about something kind of like medium difficult, right? So maybe we'll have CH3 part, right? So that is attached to CH2, another CH2. Oops, sorry. So where is the cancel? Okay, this one. Finally. So, and now we have the amine, right? So we have the amine NH2. So you think about it, so what's going on, right? So used to have NH3. So now one way to kind of like consider that situation is NH3 used to have 3 H's. Now you can see that there is a thing, the amino group, amine, right, is represented as NH2. So basically, we just need to think about the removal of one hydrogen atom, right, and switching that hydrogen atom with this alkyl chain or alkane part, right? So the nitrogen will still have the lone pair of electrons. There is only one switch, right? You remove a H with a dot, and then you technically attach CH3, CH2, CH2 with the dot being the electron, right? So now instead of H with a dot, you have this thing, the alkyl chain, as we can call it, right? So in professional terms, and then you have this like N with the dot, right? So that used to be connected to the H with a dot. So now here you have it, right? So yeah, here we go. So that's going to be your amine, right? So what are amines famous for our perspective? So let's try to connect it with the proton transfer, right? So you might maybe like rush already, which is good, right? And then show how the amine behaves. So previously, so you know that NH3 is a very good like typical base, right? So in chemistry, so which was our like, previous knowledge or is. So now since there is a similarity between NH3 and then this organic amine, right? So let's just call it amine, right? We have the amino group, which is NH2, right? And then you have the organic chain. So just call it like organic amine, right? So now this can also act as a base, right? So you need to think about the extension of the properties from one compound to other similar compounds, right? So they are called homologs in other terms. Yeah, basically it means that if, let's say, NH3 was able to act as a base, then this amine, right, with this alkyl chain will also be able to act as a base, right? So that's the structure property relationship right here. So now we can show the proton transfer. So let's just make it act as a base. So the bases accept protons, right? So we can show it this way. So as we can recall, hopefully, so I use this recollection thing quite a bit. I hope it is really the case. So we can show the acceptance of the proton with the equilibrium arrows. So now we have it, right? So we have our final product. so which you can show as such. So here you will have only one reaction center. It's going to be right here at this lone pair of electrons on the nitrogen. Everything else stays intact, right? So and then here you go. So you have here NH3, right? So and then you have the plus here. So you can also show how this like bond was made. Just it was made in the same fashion exactly as it was made when NH3 used to accept NH plus. So here you go, right? So in this situation, you also can encounter some kind of things that we saw in the past. So what is that, for example, right? That's going to be our alkane example, very good example. So it will contain only carbons and hydrogens. Alkenes are hydrocarbon, alkenes are hydrocarbons, and they do not contain any double or triple bonds, right? Only single bonds and only C and H atoms. So if you look at this part in this like rectangle here, right? This rectangular-ish region, so that will be representing a condensed formula of this organic compound, right? So you can think about the expanded ones, so in which you just need to show the bonds between carbons and the hydrogens, right? So, but right now it's like a more like fast way to like write those formulas in the condensed fashion as opposed to writing out each single bond. Okay, so now what else do we have here? So yeah, maybe I think whatever is relevant to us. Let's take a look at the actually bonding patterns between the molecules, right? So if you take a look at the example here of the amine, for instance, right? So let's say you have here these NH2 parts, right? So what does NH2 part consist of, right? So maybe for this reason, let's take a look at the like formula. In this case, let's maybe take a look at something more simple, such as CH3NH2, right? So that's going to be another homologue of the amines, right? They're called primary amines. If you see NH2 with some sort of like part, whatever this part might be, it's going to be called primary amines. But about this later, don't worry about this right now. So we'll have situation like that. So NH2, right? And then here we go. So what do we see here? So we see here the presence of NH bonds. And then if we think about the bonding between the molecules of such an amine, we need to recall the special kind of bonding, which is going to be called hydrogen bonding, right? So hydrogen bonding will be very prominent. So in this, amongst these amine molecules, right? So how can we show it? So let's now recall the creation of the so-called partial charges designated with the letter delta, right? So amine, in the amine like part, nitrogen is a more electronegative atom than hydrogen, right? So it will be pushing the or pulling the electrons towards itself, which we can show with the arrow, like so. Okay, so there's going to be like dipole moments going on. So yeah, basically, so this cross will look like a plus, right? Meaning the departure or like, yeah, partial departure of electrons, right? The bond is not yet broken, right? It can still exist because it is basically a polar covalent bond, right? So two electrons and such per bond, right? But now like nitrogen is more electronegative, and then it will be pushing the electron pair between N and H towards itself, right? So that will lend the delta minus partial negative charge, right, to the nitrogen, and then partial positive charge will be formed on the hydrogens. So now, if we want to show the hydrogen bonding, so that's not going to be a problem. So now we just need to like align the molecules in the respective fashion. So yeah, maybe we'll show the nitrogen like so with the hydrogens, right? That's going to be another amine molecule, so CH3, right? And then we'll have our like delta minus, delta plus partial charges. And then we can show this hydrogen bonding as a dotted line like so, right? So that's what will be happening. So nitrogens being partially negative will interact with the partial positive hydrogens, right? Minus and plus charges will attract. So the same principle like from physics will be applied here as well. So that's going to be your hydrogen bonding situations, right? So that's pretty much like the most important here, the most evolved. kind of interaction to show, right? In addition to dispersion forces, which are like very weak, and dipole-dipole interactions, which are in between dispersion forces and hydrogen bonding. Hydrogen bonding, I'd like to emphasize it here, just considering our short time for this practice session, because hydrogen bonding will be encountered a lot in organic chemistry, right? So then we'll be talking about this quite a bit, considering as opposed to or compared with dispersion forces or dipole-dipole interactions. Hydrogen bonding is going to be like very much useful when it comes, for example, to understanding how various reactions work in organic chemistry realm. So then what else? So that's your hydrogen bonding. So you can also think about how the potentially like if let's say we think about some sort of question, right? So will amines such as like this one, right? Like carbon, 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 NH2 will be possible to dissolve, like theoretically, this amine in water. So normally we would say, like, we have some principles again from the past, like dissolves like. The amine is an organic compound, right? So and then the water is not an organic compound, doesn't contain carbon, for example, right? So typically we can say, well, salts being like very polar, right, will dissolve in the water. Organic compounds, as we also saw from the previous slides during our presentations, do not readily dissolve in water, but they can still interact with water, right? And maybe this will lead to some partial dissolution, right? You might like speculate. So because of what? Why does it happen, right? Why can an amine potentially dissolve in water? So if we take a look at CH3 and H2 example, right? So it will have those delta plus, delta minus positive, delta plus and delta minus partial charges, right? So we can show it specifically, and then we can show the molecule of water next to that, right? So delta minus on the nitrogen right here, delta plus on the hydrogen, okay? So what about the water molecule? So the amine clearly has the NH bonds. Water molecule, if you show the Lewis structure, will be looking like this. So it will contain OH bonds. OH bonds can participate in hydrogen bonding. And then here we go, right? So same situation, delta plus will be generated on hydrogens in the water. Delta minus charge will be produced on the oxygen and the water. And here we go, right? We can show with the dots the interaction between hydrogens on the amine and oxygens in the water, right? So if you have the interaction between the solute, which is your amine, right, organic amine, and the solvent, which is your water, in this case, then you will have the chance for this like solute to dissolve in the solvent, right? Again, terms from the Gen Chem. So very important to recall those kind of like fundamental things, which is what I'm trying to draw attention to. So yeah, as long as you have some kind of interaction, so maybe it's going to be like hydrogen bonding, so which is like very legit for the solution formation. You will be able to dissolve, at least in your mind, this particular compound, right? Of course, you need to like show the like carry out the actual experiment and try to dissolve it. Like maybe you'll dissolve various amines, and depending on their structure, you will get various results, right? So some of them will dissolve more readily than others. Some of them will kind of dissolve like very poorly, right? Despite our like theoretical like considerations, right? So just a reminder here then that organically pun intended shows up is that organic chemistry in particular is an experimental science, right? So yeah, oftentimes we'll need to show the experiment to like bolster the argument of some sort. All right, so now speaking of those alkyl chains, let's take a look at the alkanes, I would say, right? So let's say what happens here, right? So alkanes. Okay, so I'm going to erase everything. We'll go to part 4. I would say we have about 10 or so minutes, so let's not make it overbearing. So part 4 here. Okay, so here is just like something that probably like was shown up as an error in organic, not in organic, but in general chemistry. So that is about It's not supposed to be new, so that's why I'm going to show it, right? So that is about the dissociation of acids. So acids can be strong or weak, depending on how readily they will donate an H plus, the proton, right? So, and then the weak acids, like big chunk of those ones was represented by organic acids. Organic acids have the organic acid functional group, which we saw in our previous discourse, right? And also they will have the alkyl or alkane part, right? So let's show this as an example. Maybe CH3, CH2, CH2 again. You have all the bonds, right? So you have here the condensed structure, by the way. So for your practice, for your review purposes on your own, you can convert this, for example, structure that you see into the expanded one, right? And then later on, soon enough, we'll get to the skeletal structures, which will be like even more condensed than condensed structures, right? So then you have this organic acid, right? So here, just kind of like take a look at the structure. So see what familiar things you see here, atoms, right? What are the names of those atoms, right? So then a tetravalent carbon, 1, 2, 3, 4, makes 4 bonds. So all good, right? Not 5 bonds or anything. So maybe show the lone pairs on the oxygen. Oxygen is supposed to have 2 bonds and 2 lone pairs, right? So show them here. So nothing new, right? You literally kind of reuse the building blocks from, let's say, water molecule, right? Or CO2 molecule, and then you just kind of like put them into bigger structures, right? So that's all it is. So just kind of like from the bricks, simple, relatively bricks, you can like build a shed, for instance, right? So now dissociation, right? So previously, what we were talking about is that, first of all, so speaking of connection of various chemistry terms, right? Electronegativity. Electronegativity difference between carbon and hydrogen atoms is electronegativity difference between C and H atoms is very small, right? So they're very close to electronegativity. So to the point that the CH bond is considered nonpolar. So what do nonpolar bonds, what are they famous for, right? So if we have a polar bond, we have a very equal distribution of the electrons, and then those electrons will like try to like rest, right, between those atoms. So it's very nice, right? So equal shared, the bond is like quite strong, right? So that's what it means for the strength of the bond. So if the bond is polar, however, then it means that eventually, or it means that the pair of electrons is pulled towards the more electronegative atom, right? Which means one of the like atoms, the one which is less electronegative, will be losing its electron. If the electrons are lost, then the bond is broken, right? It's not like 1-to-1 score anymore. So it is now 0 and 2, right? Electron score wise. So then, yeah, you don't have the connection anymore because the premise or one of the requirements for the bond to exist is that like the covalent bond, right? Single covalent bond is made of 2 electrons, in which case one atom has 1 electron and the other atom has another electron, right? So if let's say one of those atoms gets the other atom's electron, then there is no bond anymore, right? And you have 2 separate particles. So which should make you think about, for example, HCl. So that's what happens, right? HCl bond is broken. That's when dissociation, right? So this disconnection, dissociation takes place, and you have now 2 particles, H plus and Cl minus in the case of HCl dissociation. Here, very similar thing will happen, right? So if you look at this, considering the GenChem 2 experience, I would say, right? So that is an example of the acids. So as we recall, so the CH bonds don't dissociate typically, so because they're very non-polar, but the polar bonds will be weaker typically, and then they will have a tendency to dissociate because of this kind of like electron pool, right? So yeah, that's it. So that's what is going to happen, right? So the OH bond is polar, right? So because there is a big electronegativity difference, you can like for your, let's say, homework review purposes, you can feel free to use the periodic table, the dynamic periodic table, as we call it, I'll try to put the link somewhere in the presentation slides down the line. So, and then you will see the like big electronegativity difference once you hover over the respective elements between like O and H. So the OH bond will be broken. We can show it this way. So that's going to be the cleavage here going on of this bond. So these ones will stay intact, right? So considering that, yeah, the hydrogen, the acid is supposed to produce H plus. So we have only like two places to like potentially get it here or here. CH bonds are nonpolar, so we leave them alone, right? So they will just stay. And then, yeah, if you want to show dissociation of this acid, it's going to be quite easy. So you will have your alkyl chain, right, or alkane part intact. So just kind of redraw that. You'll have the practice of, let's say, drawing those alkanes, right? So everything else is a copy-paste, basically. So you just need to be careful about, okay, I can even put it into the color. Let's see, where's the color? Let's make it red. So this electron pair, right? So what's going to happen? So that's going to be quite interesting. So we'll have H, right? So they're dissociated. So electrons are not equally broken, right? They are heterolytically broken. Hetero means like different, Greek lysis, different breakdown, right? So anyway, so now we can also, so if you want to be like professional, we can show the pushing, right, the transfer of the electron pair towards oxygen. So what do I mean by this? So then I can just go ahead and then show this two red dots on oxygen. That's it. That's all that happens, right? So like in a sense, you can just think about only one electron loss, right? So by hydrogen, but by convention, this arrow, right? So this arrow with the red head here shows the movement of the pair, right? So in a sense, the pair is now, first it was shared between O and H, now it is completely on O, right? So you can think about it as movement of the pair, right? So just think about it like in the privacy, let's say, right? So now, okay, what happened is charges are generated. Hydrogen used to be just an atom, but now it is H plus, that's our proton. So this is, if you don't want to call it, you can call it at least the anion, right? Or counter ion. More specifically, anion, just negatively charged ion, right? So, and now you have the charge, right? So O used to be just a neutral atom. Now it gained one of those extra red electrons. You have now the minus charge. So you now properly showed dissociation of the organic compound, so specifically an acid that contains the alkane chain, which is something that we have seen already, right? At least for like one presentation. And you also show the this functional group in action. It functions as the kind of like proton source and behaves as an acid. So yeah, pretty good, right? So then what else? Maybe let's just take a look at some like isomers, right? So which again, I'll just kind of like get the ball rolling, and then you can like, if you have time, you don't have to have like 2 hours, right, to draw them. So it's much less than that, and will take less time than, let's say, scrolling, right, potentially. So yeah, so let's say, okay, well, speaking of scrolling, right, so we need to scroll to item 5. So here we go. So isomers, right? So just maybe like doodle an isomer, right? So you will practice the writing of the expanded or condensed formulas, right? Maybe at this point. So if you have drawn several expanded formulas, you might be like tired of those like, showing every single CH bond. So just do something like that, which is going to be the like officially called the condensed formula, right? And then make some kind of like long structure. So maybe let's make something more difficult this time around. And let's maybe like show a huge alcohol, right? So OH. So that's the one, right? So that's one molecule, right? Which, due to its like huge structure, can potentially contain isomers. So how can we build isomers? So one of them is just, okay, go ahead and then do the branching, right? So here, what do I mean by this? Again, so we have a just straight chain if you look at this, right? So just look like a straight line of atoms. So now we can make the branch, right? So we have 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 carbons, 5 carbons and oxygen, right? So let's maybe make it shorter, right? So let's make it like 4 carbons. So let's show them like this, right? But we must not lose the carbons in the isomer because the elemental composition stays the same, like CXHYOZ, right? Whatever like X, Y, and Z numbers are. So then that's the condition for the isomer. So the brute formula or the molecular formula should stay the same, or must, let's say, but we can move around the carbons, right? So, and then maybe let's leave that oxygen here, connection everywhere, right? So then we can put the like oxygen or carbon like here, let's say, right? So that's it. So these are our bonds, right? So then we need to like populate them with the H's, right? So if you think about that, carbon must have 4 bonds, right? At all times. So in the neutral compound. So here we have already 2, here is 1, right? Here is 3, right? So now oxygen has 2 bonds. So now we're going to still have our H here, right? So we run out of the carbons, 5 carbons, 5 carbons, 1 oxygen, 1 oxygen. Now H's, count them wherever they are, so they have to be translated into the isomer, right, that we are writing here below. So if you have carbon with 1 bond, just kind of like put, for example, 3 hydrogens here, right, provided you don't have any other atoms. If you have the carbon with 2 bonds, you can make it CH2, not CH3, not CH, right? Because of what? So because you have 1, 2 bonds, 3, 4, since you have 2 H's here, right? So you are good. So same with this atom too, right? So this carbon is a little bit different, right? It has 3 bonds. So consequently, we can only give it 1 more bond, right? And considering that we don't have any other atoms to choose from, we can only use H. So that's your CH group, right? Finally here, 1 bond, so 3 more bonds are available. So let's put 3 H's on it. So if you look at this, right, so you have the isomer. So just count the carbons, count the H's. If X, Y, and Z, right, for like CX, H, Y, O, Z, check out, right, or are equal, then you have the isomer, right? So very good. So now pay attention to some groups, right, which you will see specifically in like various compounds, as you might sense already. It's CH3, right, will have a name to that. CH2 group will have a name to that, and CH group will have a name to that. So methyl, methylene, methine. So I'll just kind of like spell them maybe. So, but we'll talk about this down the line. So it's a little bit like in advance, but it's good to be methine. How do you spell it? I think it is methine. And methylene. Okay, so yeah, I think that is kind of the situation here. So these are the groups, right? Which, and then those names, the words will be used. You might encounter them somewhere. I didn't encounter them after taking organic chemistry courses. So yeah, maybe you'll be fine. So, but yeah, just something to keep in mind, at least for the mind and memory and skills development, right? So you can use that as a perspective, right? So here you have your like OH group, which is going to be called the hydroxy group by itself, right? In organic chemistry, it's COH, so this like formation together is going to be known as then alcohol functional group. And of course, we have the like alkane functional group like right here. So it's our big like alkane chain, right? Alkyl chain. Alkyl is an adjective. So alkane group, alcohol functional group. So like very nice. And then these are 2 isomers, right? So you can think about kind of like making a whole different functional group from here, right? So maybe let's make this so-called ether, right? It's COC. So we can just put this oxygen randomly somewhere between carbons, but we need to like follow the valences, right? So let's make it happen. So sorry, so that's way too fast. Cancel. Right, 5 carbons in a row, right? So we have 3, and then let's put the oxygen here, and then C and C. We'll make it like straight chain. So oxygen, you see, already ran out of valences. So only 2 bonds are on oxygen. 1, 2. 2 bonds are engaged. So now let's take a look. So this C with double bonds looks like with, I mean, two single bonds will look like CH2, another CH2. So then you can like try to be fast in practice, right? Then correct mistakes, right? So because the stakes are low here, then this will look like CH3. And this atom will look like CH3. So now count your carbons, oxygens, hydrogens, right? As long as the X, Y, and Z numbers for carbon, H, and O check out with this original compound, which was like this one, right? Then you have another isomer. And you have kind of different structure, right? So you have no more like COH, which is an alcohol. You have the COC formation, which is an ether. So which is like pretty nice, right? So now you have here kind of this kind of like ether, 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 ether functional group, right? And you have, of course, the like alkane. I'll just show it in circles. Another alkane here, right? CH2, CH3, CH2, CH2, CH3, another alkane. So I think that's kind of like enough of taken out of the brain, as people say in Eastern Europe. And at this point, we're going to stop the recording and wish you have a good day. Okay.